try to raise your hand. I got stood up for this.
Okay.
Because then if it's not working for you, then...
All right, we're going to get started. So what I'd like to do is start the day with just some grounding on the comparative cohort analysis design. Just a basic overview of what we're trying to accomplish and how we think about the problem. A lot of this, there are some things that I'm going to say that are just a statement of fact. There are some things that I'm going to state that are potentially an OHDSI opinion. Most of what I'm going to state is not an opinion or a judgment. It's just a framing of how to think about the problem. One of the biggest observations I've had in this space and working with, including working with Ermila over the last several months, is that as a community, we use different words to describe the same concept. And sometimes we talk past each other because we're using the same words and mean different things. So what I'm going to use this morning to do is ground us in language that we can all be using together to describe what we're doing. And I encourage you to use that language for the purpose of the exercise, just so that we're grounding ourselves. And then as we go through the day, you'll see how that kind of fits into pieces. All right, so let's get started. So, all of you heard yesterday, hopefully it's abundantly clear, we are here because we are all sharing a mission, which is to improve health by empowering a community to collaboratively generate evidence that promotes better health decisions and better care. And so this course specifically is focused on one type of analysis to generate one type of evidence, but ultimately it's the evidence about making a decision between alternative treatments. And we think that that directly fits within this remit. So you heard us talk a lot yesterday about clinical characterization, population level effect estimation, and patient level prediction. So today's scope is restricted in the population level effect estimation. Not to say that the other stuff isn't good and cool, it's just that that's what we're teaching you today. Across those questions, I see some questions that really would fit into the safety surveillance kind of realm. Like I think, Nicole, your question is more oriented to, does SGLT2s cause UTI as a potential side effect, whereas a couple of those other ones look like they might be more in the comparative effectiveness realm of trying to understand relative differences. Both of those are valid, and in fact, the methods that one would use for those two different questions are in fact the same exact methods. And so we're going to genericize this to talk about effects of exposures on outcomes. But just in mind, if you're thinking, oh, I want to do safety, or I want to do comparative effectiveness, that all falls in the same bucket. So the strategy that OHDSI has had in terms of how we're delivering evidence is we do three things. We do methods research, we do open source software development, and then we try to generate evidence to clinical questions that matter. This tutorial really is bridging all three of these because it's the methodologic research that's been led by Martijn and Mark and others that we think we've learned a lot to know about best practices. We've then codified those best practices in open source software that you're going to be able to play with. The designers are going to be using web-based front-end tools that you've seen called Atlas. The programmers are going to be using R packages that have been developed. That's just all open source, freely available code. But ultimately, you guys have the most important job, which is to generate evidence to real clinical questions. So the reason we have that on the board back there is I want you always to be going back to, how am I going to generate evidence to a question that matters to a patient? That's what we're trying to do. All of this stuff is just to enable you to be able to do better research. So, if we think about a standardized process for evidence generation and dissemination, we could think about this seven steps. First and foremost, you want to have a question. You want to know what clinical question would matter to patients. From there, you want to review what is already known. Is there evidence that exists in the world? So I know many of you, as you're preparing your question, you started to look around and say, like, has this question already been answered? Maybe what's the deficiency of what we know? What is your prior belief about that question? Like in Nicole, in your case, you had mentioned like you've already done some work in some other data, so you have a bit of a prior belief of what might happen. Based on that prior belief, we want to design a study that's going to most effectively answer that question. And the design component is really what I will be focused on in the class today. From there, you should stop what you're doing and publish a protocol. You should write down what your design is, specify all the choices you're going to make, produce a document that says, this is what I'm going to do to generate evidence. At that point, once you have specified what you're going to do, you can move forward into the execution phase. And the three things that we would advocate is that you want to execute the study, which means implement what is written in the protocol, exactly what's in the protocol. If the protocol is written properly, execution should be nothing more than following the set of instructions. The next step, which you heard a lot about yesterday in the main sessions, is you want to evaluate your execution. You want to know, now that I've designed this study and I've run and I've generated results, how much can I trust those results? We are going to just continue to allude to how to do evaluation throughout the course of the day, but this tutorial is really going to be focused on the design and execution. The evaluation will be subsequent tutorials. So we're going to tell you where you should be fitting that in, but you're not going to actually get to do too much of it during the course today. And then last but not least, you should synthesize your prior beliefs with what you've now generated as new information to revise your thinking about what is the current state of evidence that you want to communicate. All too often what we see in the literature is, in terms of deficiencies in this process, is there aren't all that many protocols that we actually see floating around the world. We see lots of people making lots of different judgment calls on designs that may be arbitrary. We don't see the code that people execute, so we don't have very much transparency into that. Certainly evaluation is a new paradigm as it relates to effect estimation. But the other thing that I see as a critical issue is all too often we see observational studies done where someone had a question, they ran a study, they produced a point estimate, they published a paper and said, that's my point estimate. But I think that's a really important point is that if you wanted to think about this as there was a wealth of evidence, you are adding new evidence on top of that. What is your current belief? It really requires that synthesis to be able to put that together appropriately. So at the end of today, if everybody gets through all of the exercises, you will have run code and produced a number. That number is probably publishable, but it should not be published until you have actually properly reviewed everything that's already known and synthesized it with what you've now generated. So how is OHDSI trying to help that process? I probably don't need to be on Skype anymore. So how is OHDSI trying to help this process? So we want to be very clear. As a community, we want to work together to come up with questions that matter. When we talk about reviewing the evidence, you heard a little bit yesterday, and hopefully you saw during the demos, Laertes is an open knowledge base of information from literature labeling spontaneous reports. The design component is going to be enabled by some tools that we're going to show you today. The execution is going to be done by the entire methods library that Mark and Martijn are going to go through. And then ultimately, when we think about synthesis, one of the biggest opportunities we have as a community is we no longer need to be limited to running our one analysis in one database to produce one answer, but we have a network so that we can replicate our studies across multiple sites, which we think should be part of the synthesis process. All right, so now what I need to do is explain counterfactual reasoning, and I know that all of you have probably heard this in various ways, but probably never quite like this. Anybody recognize that picture? Who's that? Keanu Reeves, Neo from The Matrix. How many people have seen The Matrix? Most people. Okay, good. So in The Matrix, there's this moment when Neo is provided the option of taking the red pill or the blue pill. And at that moment in time, he's told that if he takes the red pill, he's so if he takes the blue pill, he's going to go into this dimension and learn how the world really works. And if he takes the red pill, he can go back to his little simple life and never think about it again. And so what we know happens in The Matrix is he grabs the blue pill and the rest of the movie continues forward. The thing is, we don't actually know what would have happened had he taken the red pill. He was told what might happen, but we didn't actually see it. The issue with counterfactual reasoning is that all of us face decisions in our lives of whether we're going to take the red pill or the blue pill. And we make a choice, and then we move on with our life after we've made that choice. The issue is we don't know what the alternative universe, that alternative matrix would have looked like had we made an alternative choice. So to rationalize it a little bit further, you're a person, you're living your life, and you're going through your trajectory of your patient journey in your life, and you're faced with a decision, red pill or blue pill. At that point in time, you're going to make a choice. You're going to choose to take a red pill, and then you're just going to continue on with your life. At some point in time, some outcome might be experienced. And so you could say, well, I took the red pill and I had an outcome. I took an SNRI and I had a suicide. I took a sulfonylurea and I had a colorectal cancer. And that might be absolutely correct. But if what we wanted to do is produce a valid study, what we would need to do is grab this person, drop him into the DeLorean from Back to the Future, fly him back to the exact moment when he swallowed the red pill, drop him off, and make him swallow the blue pill instead. If he swallowed the blue pill, he'd go on with his life, and this alternative universe would happen, and at that moment in time, some alternative outcome might be experienced. It might be the same outcome, it might be a different outcome. If you could do this, if we had a DeLorean, we'd be able to actually produce a valid assessment of a causal inference. We would know that the only thing that's different up to this point in time is just whether or not you took the red pill or the blue pill. So this picture is going to be important, and it's actually going to frame some of the questions we think about. That decision point, whether you're going to take the red pill or the blue pill, that is the moment that we are going to think about our causal contrast. So we're going to think about that as time 0 on a person's life, and we can capitalize on information prior to time 0 as a way to understand a person's life, and we can think about what happens after time 0 as the follow-up, when the outcomes could be experienced. So for all of your questions, what I want you to be thinking very clearly about is what is your decision, what's your red pill and your blue pill, and what is that actual moment in time when that decision is being made, because this is going to be an anchor at everything that we're doing. Now, of course, there isn't just one person who's going to go through their life. There are lots of different people who are making lots of different choices, and so lots of people are going to be of different styles, taking the red pill. We'd like to send them all back so that they could live their alternative life, going through and having different outcomes. And if you had a population of people who all could go back in time and live their life again, then you could produce a population level estimate of what the effect was. Because you would know that there was a collection of people who took the red pill, and you'd have all of their outcomes. And you'd also have the exact same set of people under the alternative condition that they swallowed the blue pill instead of the red pill, and you'd be able to look to see what their outcomes were. This would provide us a very clear contrast of the exact same people at the exact same moment in time, and what was the alternative attributable to red pill or blue pill. All with me so far? All right, so one little limitation. We don't have a DeLorean. We can't go back in time quite yet. So what is our next best approximation? Well, what we typically will talk about in a lot of the work that we'll do is we'll think about how we could randomly assign patients to one treatment or the other. And so what we could think about is having a set of people randomized to take the red pill and a set of people randomized to take the blue pill. And in that concept, what you actually are having is that a given person who has been randomized to get the red pill, they're assigned the red pill, and you're going to see what happened to them after they took the red pill. You're not going to observe for that person what was happening on the blue pill. But you hope through randomization that if you create two populations, you're going to end up with a population that is sufficiently comparable to the population that was equally randomized to the blue pill. And so what you're doing is you're drawing a contrast between what you can observe in the assigned to contrast there. Now, randomization allows this to be possible based on an exchangeability assumption that we think that the group of people that were randomly assigned red are exchangeable with the people that are assigned blue. So we've got another problem. We're all here because we're observational data researchers, and we can't randomize. We don't get to decide the intervention for a patient. So what's our next best approximation? Well, the approach that we can take is we can define a larger population, observe the treatment choices that patients have actually made, and then try to compare outcomes. There are multiple different designs in this space. Today we're going to talk about a comparative cohort design, which is going to be a contrast between people. However, there are also within-person designs that we also have done quite a lot of work on. This tutorial is going to be on comparative cohort design. Just to be crystal clear, we're not advocating for this design as the right way to do a causal contrast. It's just one approach that people are using, and subsequent tutorials will be focused on the self-controlled designs. The one thing that I want to reinforce here, though, is that sometimes you'll hear or see in the literature people say, our goal for an observational study is to approximate a randomized clinical trial. That's not correct. Our goal is to approximate causal inference. It's to approximate the DeLorean. It's just that we can't do that. And so a randomized clinical trial is in itself an approximation of what we wanted. An observational study is going to be an approximation of the approximation. And I just want you to be thinking about the actual problem that you want to solve, because it's going to be related to, can you really legitimately make a valid comparison between the two groups that you're studying?
If you have a comment, the way Patrick's framing this is critically important here. So in the epi literature and in epidemiology textbooks, they don't frame it like this. And I think it leads to a lot of fuzziness and murkiness and so on. It is all about causal inference. It's all about trying to recover what would have happened had they taken the other path. So this isn't a small point. This is critically important. This is the basis for everything to follow today.
Oh, and I apologize. I should have actually formally introduced the faculty. So, I'm Patrick Ryan. We have Martijn Schumi, Mark Suchard, and David Madigan. We're all going to be tag teaming this throughout. So I'm going through material, but do stop us, ask questions, challenge us, and we will all be chiming in too as we go along. And we're also going to be all wandering around helping you with all your exercises. Okay, so how does the field of epidemiology define a comparative cohort study? It totally depends on what epidemiology textbook you decide to pick up. My boss has a bookcase full of epi textbooks, and so a couple months ago I went and I just cleared his shelf of all of the epi textbooks, and I went to the section that said cohort. And I was like, surely they're all just going to be redundant stuff. But actually, I couldn't find two textbooks that actually had the same definition of a cohort. So I'm going to go through a few of these definitions, and I want you to be thinking about, actually just first quick, just show you guys, how many of you think you know what a cohort is? Okay. Most of you. Okay. I guess I shouldn't have set it up with you don't. So I'm going to go through a few of these alternative definitions. Again, this is about framing. It's not that these are right or wrong. They're just using different language. And I want, as I go through them, I want you to think about, is this the way you were classically taught what a cohort study was? So in the Kelsey textbook, it described that a retrospective cohort study, the investigator identified the cohort of individuals based on their characteristics in the past, and then reconstructs their subsequent disease experience up to some defined point in the most recent past or up to the present time. Just show of hands, how many feel like that's kind of what they think a cohort study looks like? 1 and 1.5. Okay. Fletcher, and Wagner define a cohort study as a cohort study is a group of people, a cohort, is assembled, none of whom have experienced the outcome, but all of whom could experience it. And on the entry to the study, people in the cohort are classified according to these characteristics that might be related to the outcome. These people are then observed over time to see which of them experience the outcome. How many of you are Fletcher, Wagner fans?
Not the whole thing.
I mean, it's all flavors.
Yeah, not the
They're
whole
all
thing.
hitting around the target.
Okay, so
Some.
okay.
Come on, Michael, you gotta pick one.
Wait till you see them all.
Laszlo and Nieto describe a cohort study's most representative format. A defined population is identified. Its subjects are classified according to exposure status, and the incidence of the disease or any health outcome of interest is ascertained and compared across exposure categories. Something like that.
That's more of a
Some parts.
This one's got a little bit of a comparative effectiveness kind of bent to it, yeah? Well, we've got a couple hands on that one, maybe? Yeah, okay. Brian Strom defines cohort studies are studies that identify subsets, plural, of a defined population and follow them over time, looking for differences in their outcome. Cohort studies generally compare exposed patients to unexposed patients, although there can also be used to compare one exposure to another. How many like Brian's approach to the world? Ooh, more hands for Brian, okay. Our friend Ken Rothman defined it as, in a cohort study, the investigator defines 2 or more groups of people that are free of disease and that differ according to the extent of their exposure to a potential cause of disease. These groups are referred to as the study cohorts, plural. When 2 groups are studied, one is usually thought of as exposed or the index cohort, those individuals who experience the putative causal event or condition, and the other is thought of as the unexposed or reference cohort. I mean, like the Rothman definition.
Except the disease really is outcome in a more general sense.
Yes.
More general.
Yeah. Disease. Yeah. Be outcome. Yeah. Okay. So Michael, you pointed out, and it's important. They all kind of are similar. They're kind of, but I want to point out a couple of the key differences in these definitions. One thing is that sometimes people think of a cohort, a comparative cohort study, is you define a cohort. So it's one population, and then within the population, you classify the individuals of the population as exposed, unexposed, outcome, not outcome. That was kind of in some of those definitions. These last 2 definitions actually think of the world as 2 cohorts. That is, you define the group on the red pill and the group on the blue pill, and then you're comparing those. It is logically the case that those things can be, those are exchangeable. You could think of it in either way. It's just a matter of whether you said the cohort of blue and the cohort of red, you smush them together to give you one big cohort, or if you think of it as you have one big cohort and then you split them into the blue or the red. For purposes of language and for framing, we are going to think of a comparative cohort study as 2 cohorts. So we're going to kind of follow this Rothman definition. Okay? That is, there is going to be a target cohort, the population of interest, and there's going to be a comparator cohort. If you all want to think of the world as one cohort outside of today, that's your business. For today, think of the world as 2 cohorts. I think we're going to convince you that this is going to help greatly in clarifying how you think about some of the decisions you make if you think of this as 2 cohorts. And we'll get through that in the course of the day. Which
And so is it trying to, let's say the blue pill is not being sold in Japan, and I'm having some red pill cohort in Japan. So is the assumption that at least the red person had a choice to take the blue pill at some point, or it doesn't matter?
Yeah, so you're hitting on the spot on. Actually, just a technical check for the room. Are we all getting the sound for everywhere? Okay, so we're good. Okay. So you're hitting on the heart of the issue. If we want to answer a comparative question, that means that a patient is facing a decision. That means that that decision needs to be a valid one. If a patient only has a choice of the red pill, they can't possibly get a blue pill, then you should not try to draw a comparison between the red pill and the blue pill. That would not be a valid comparison to make. This is a critical issue that comes up time and time again, in that people will try to compare 2 groups when fundamentally they're comparing things that are not actually at that decision point. Now, you could think, when I say red pill and blue pill, think of that as an intervention of any sort. And an intervention could be, don't take the red pill. So that's a viable thing. We're going to talk about just constructing a cohort. But if you are going to compare 2 things, it should be the case that a patient has a logical choice, because you want them to take one of those choices, jump in the DeLorean and come back, and take the other choice. That is the causal inference that you wanted to draw. Mary.
So I just want to make like kind of a point/question. So I know I always learned the Rothman definition only in the context of like survival analysis, where you have this index and then you have the exposure. But I think that in a way, it does make sense to look at a cohort as including other people, not just the people who choose the blue and the red pill. And the reason for that is, if you just look at the blue versus red pill, suppose you find that the blue pill causes depression or something, but in reality, it's that the red pill is protecting you against depression, and the blue pill is actually only experiencing depression incidence that's normal to the general population, as in the people who don't receive either blue or red pill. If you focus only on the blue or the red pill, the inference or the conclusion that you make may be the wrong conclusion, if you don't look at the whole kind of larger level cohort of people in the kind of universe or space of people. So when you focus in on this decision, do have to kind of at some point bring it a little bit higher and compare the incidence to a global or reference population. Otherwise, you could get the backwards, you could get the conclusion backwards. And I think that might be what you get at the synthesis step of your
That's right.
of
Yeah, so we
section.
want to create a valid causal inference. It is a valid causal comparison to compare red and blue. How you then interpret that difference, whether you say red is worse than blue or you say blue is better than red,
Yeah,
that regardless, it is going to be a valid causal inference to compare red and blue.
I think that some of those earlier definitions were trying to get at that idea by looking at the cohort as like, cohort is the universe or space of everyone, and then you kind of subset into people get red or blue, or people who don't get anything, or people who get this other green pill, and so forth. So,
So do you guys have any solutions for like if there are 3 pills or multiple?
So yeah, how do you deal with the fact that there are multiple turns? Ultimately, what we're going to focus on for purposes of today is you are making choices between 2 options. You can actually, what Martijn showed yesterday is you can permute all pairwise options. There is a very small amount of literature about how you can just logically extend everything you're doing into the multinomial space, but realistically, usually everything does come down to a choice of A or B. It's just a question of how you want to define what your B is.
But there's nothing, the framework extends, and there's nothing.
Nothing magic there.
How would you define these patients? How can you identify the patients that will be receiving drug A because there is some reason not to receive drug B?
So there's a perfect lead. So what we're going to go through today is, given that I'm now framing the problem as we're going to create 2 cohorts. You're going to create your red pill and your blue pill, and we're going to study an outcome, which is something in the past. From all of you who are the designers, we're going to focus on exactly that question. How would you actually go about finding the people who took the red pill and finding the people who took the blue pill and finding your outcome? And from a programmer perspective, it's going to be how do we actually run statistical models? Given those inputs, how do we define that? So that's exactly what we're going to do all throughout the day.
And how do you separate the ones that were enriched? Because some underlying reason that the data may not.
And that's exactly what we're gonna. That's what today's. You're in the right room. That's exactly what we're covering all today. All right. So that observational comparative study, what that basically looks like is you've got your people who made their conscious choice to choose the red pill. So you don't know what would have happened if they took the blue. And you've got a different group of people who took the blue pill, and you don't know what would happen to them when they took the red pill. And so, to Anna's point, one of the challenges you get is it could be that the people who took the red pill just fundamentally look different than the people who took the blue pill. And so therefore, when you see differences in outcomes, you don't know whether the differences in outcomes is because of the treatment or because these people are different. Okay? So the big thing that underlies all of this is there's this exchangeability assumption that's going on that can be violated, that if the people are not in fact exchangeable, you are going to lead to an invalid inference. So, does anybody in this room recognize those little characters?
Zelda.
No.
How is that Zelda?
This is ice hockey from Nintendo.
I have to have the Canadian to be able to figure out ice hockey from Nintendo. These are ice hockey from Nintendo. Did anybody ever play original old school Nintendo ice hockey? Just one. Oh, I haven't got one? Yes, awesome. Okay, so I'll explain very briefly. The way that this old school game worked was you got to choose your team. Your team was a country, which was a color, and you got to choose a lineup. You got to choose skinny, mediums, and fats. Okay? And anybody who played the game, and my guess is, Jamie, you must probably the same way. You probably remember what was your optimal lineup. I was 3 skinnies and a fat.
I can't remember. I think it was something like that. The fat guys could shoot well.
That's right. So everybody, like some people were 3 fats and a skinny, some were 2 fats, a medium, and a skinny. I was a 3 skinny and a fat. The key, though, was that everybody who played this game made a conscious choice of what their population was. It was a rational choice, and when you competed, the whole point was that I picked my strategy against your strategy. This is a direct analog to our situation. There is a conscious choice that's being made of why people are getting the red pill, and it's a different conscious choice than why people are getting the blue pill. So we are going to try to create a causal inference knowing that someone actually consciously made this choice in this construct. And I made a bet with Martijn that nobody would know this reference to this video game, so I now have to take it out of the tutorial next time. But I'm glad that one Canadian knew it. All right, so there are many different strategies people take to try to solve this. We are going to describe one today, which is propensity scores. Show of hands, how many people feel like they know what a propensity score is? Okay, how many people feel like they know it well? Okay. So, basic idea, propensity score is just a probability of treatment assignment conditioned on all of the baseline covariates. We are going to use it as a balancing score. We're going to try to make those two populations similar on the basis of all of their baseline characteristics. The one thing that we're going to focus on when we talk about this is that you need to perform diagnostics to actually ensure that you're doing this well. And Martijn showed some of them yesterday, and we're going to get into more depth about exactly what those diagnostics are and how you should use them. Very importantly, there is an active debate and discussion about the right way to do propensity scores. I'm going to follow the original Don Rubin thinking about things, which is very explicitly, you can use everything in the past as a baseline characteristic. You're not supposed to cheat and look forward. Okay? You will read some papers where people say you actually really should put covariates that are related to the outcome in your model, not the exposure. The propensity score is a predictive model to predict treatment assignment. Its goal is to predict treatment assignment. You should be trying to predict treatment assignment. Conflating that with issues associated with what are your outcome covariates is not what we're going to go into. We will be able to assess whether or not there are other covariates that are going to go on. But for this purpose, think about this as a prediction problem, just like what Peter showed yesterday. And the prediction problem is, are you a red pill person or are you a blue pill person? And our objective is predict that question as best you can. Go ahead, Mike.
I was just going to make a comment. So I think they're slightly separate issues. One is using only data prior to the index date, which you were totally. Yep. The other issue is choosing predictors prior to the index date that you think might be related to the exposure and the outcome. A lot of literature does. I think that's a reasonable. Are you saying that you only want to choose predictors based on the likelihood of predicting the exposure and not the outcome?
I want to predict treatment assignment as best I can. I'm not trying to solve a multivariate objective function saying I want to manage them subject to forcing some variables in the model or not using other variables. This task is a prediction problem to predict treatment assignment. We'll get into the issues of covariate selection and whatnot. I think ultimately the end game is going to be you're going to get everything you want anyway, but you shouldn't go into this prediction problem thinking about your outcome. You should go into this prediction problem thinking about the task is to predict treatment assignment.
Question and slash comment. Propensity scores, my big problem with even throwing all the knowledge I have in my database into it to build this particular propensity score, it's still a model at the end of the day. There's a limitation of how good is this model. Second, the most important contributing factor to that is what data goes into that model. Meaning, you may have 40,000 variables, but it's only 40,000, and how do we know that there's something really, really important that's captured in that 40,000 or not?
Yep. So you're in the right place, because that's exactly what we're going to focus on, is explaining how we need to systematically apply diagnostics and evaluate the answer to the question, how good is this model, and how much you can trust the evidence that comes out after using this model. That's exactly what the focus of the diagnostics and evaluation is. Okay, so since you all know this, I'm going to just skip very quickly through. The idea is that you can have a distribution of propensity scores. One important thing, and it goes back to Wojciech's question, is if you were to plot a probability density function of the red pill and the blue pill, you might find people who only are eligible to get the red pill or are only eligible to get the blue pill. That means that those people have no logical counterfactual. There is no probability that if you're way out here, there was no chance you were going to be a red pill person. Or if you're way over here, there's no chance you would be a blue pill person. This matters as it relates to the causal contrast, and that's why you will see people talk about ensuring propensity score overlap, is because there is no information here to compare red versus blue if you're in a situation where all those people are only reds or they're only blues. We're providing you all of these slides. A lot of this is just reference material in case you are looking for backup information or things to put you to sleep. There is a paper by Glenn et al. That talks about the advantages to why you should use propensity scores in pharmacoepidemiology. I'm not going to actually belabor any of those points, but refer you to this paper if interested.
Back to the previous slide I had, just to make sure I understand something about the model. So, in the retrospective data, someone either did or did not take a given drug. So, if we had infinite knowledge, we could essentially say you took this or this.
Okay.
So, is the process essentially some sort of a cross-validation where you're making sure when you're assigning a probability to someone having taken a red or blue that we haven't looked at their data essentially to make that prediction?
Yeah, yes, you can frame it that way. So if you want to think about it as your probability, your propensity score is your probability of treatment sites, your likelihood of being a red pill person or a blue pill person.
But the thing is, it's either 1 or 0.
Every person is actually a 1 or a 0.
Yes, when you say the probability, you're saying I have a model that have somehow looked at the data and built a prediction on these. And
Yes.
so what I'm getting at is how are we not, making sure we're not overfitting or something and assigning essentially perfect probabilities to the two, because we could.
So if it were the case that there was observable, meaningful differences between the groups, one of the things you would expect a propensity score to do, or a prediction model to do, would be to separate the groups. Find out why there's red people and why there's blue people. What we are actually predicting is that 1 or a 0. They actually are a red or a blue. That's what we're trying to predict. But we're trying to predict that using all of the information in the past. Two things can happen. One is you don't have the data to actually do that discrimination. Or the second thing, it could be that there are 2 patients who are really identical in every way, except that one arbitrarily the doctor gave a red pill and one arbitrarily a different doctor gave a blue pill. In which case, that person, if they were identical, is kind of close to that approximation of the randomized trial that we're trying to emulate as our first step back.
When you are saying patients that probabilistically they would have never been treated with a study with a red pill or with a blue pill, why not include them also in the assessment?
So,
instead of having only 2 groups, the one that overlap, why don't we understand what happened with the patients that they have a unique propensity to receive either the red pill or the blue pill?
I mean, so the whole point here is to try and mimic the counterfactual, right? So, we're trying, the people, somebody who took the blue, let's say it's let's say it's an oral contraceptive.
Yes.
Right? So, let's, for argument's sake, let's assume men don't take oral contraceptives. So if there's no causal contrast there. So if it's a man, they couldn't have taken it. So you can't create the red-blue contrast.
Yes, I understand, but it will give you useful information.
It's sure, but it's, I suppose the question we're focused on here
Yes,
is a very narrow question of red versus blue.
I understand,
Could
but
be
in
on
general,
compare.
it will be very useful to understand why they
Yeah,
are different.
so yesterday we really harped on the idea that there's characterization to study populations and understand what's happening. There's estimation to get valid causal inferences, and there's prediction. So what we're focused on right now is that causal inference, but that does not mitigate the fact that you would want to characterize these people. You absolutely do want to do that. You just can't draw a causal inference from
That's
it.
right, that's right. But it can provide you useful
Oh yeah,
information.
sure.
Yep. Okay. So, how do you use a propensity score in practice? So there are many different methods that have bounced around in the literature. There is regression adjustment, matching, stratification, inverse probability weighting. Some people are using these in other mechanisms. Just for framing, while regression adjustment was talked about in some early literature by D'Agostino Jr. and others. I think in general right now the consensus is this is not a sufficient strategy for adjusting for differences, but you'll still see it dancing around in the literature because old habits die hard. Don't do this. What we are going to focus on today is matching and stratification as two different approaches. These are fully implemented in the OHDSI tools. You will see papers where people are doing weighting. Our tools could do weighting if we wanted to. We're not casting any very specific, explicit judgment about it, other than we're going to teach you matching and stratification. So the idea of matching is that I'm going to go through this example. So the idea of matching is we had our green people and our red people, took the red pill and the blue pill. Matching is the idea that you find the person who has the same propensity score. You find those people matched up. We're going to explicitly remove the people that don't have matches, and that way we can draw a contrast between two groups that are different people, but they're at least similar on the basis of that propensity score. Stratification is the idea that you're going to preserve the populations, but you're going to bin them into groups that we can study. So basically we're going to take all the larges, the mediums, and the smalls, and we're going to specifically create contrasts within each of those groups and then try to find a way to study across the contrasts. Okay. These are choices that you, a designer, get to make about whether you want to do matching or stratification. What we're going to impress upon you is that you should at least evaluate it to figure out that it's actually doing what you hope it's doing. Okay.
So matching, are you just finding a one best match? Sort of like a paired design?
So throughout the day we'll go through all of the specific details of how to do matching, but you could do a one-to-one matching. You could do a variable ratio matching, so you could just find multiple people. And then how you choose who's close enough is another design choice you get to make. Are you looking for someone within a fixed value of that propensity score or some relative value? Those are choices that you have to make and often are not adequately specified in design studies. So we're going to implore you that if you have to make a decision, you got to write it down. So we published a paper out of the original OMOP experiments that looked at the comparative cohort design. And our research on this was fairly tempered. Tempered is probably a good word. So we are providing this course not because we think comparative cohort is the right thing to do in all circumstances. In fact, our study actually showed that the comparative cohort design has a huge number of design choices, all of which can matter spectacularly in influencing your effect estimate, and most of those design choices are pretty ill-specified. More pressingly is that this design explicitly requires choice of a comparator group, and that choice actually influences things very hugely. So what we observed in our studies was that this method has poor operating characteristics. Basically, depending on your choices, it could be highly negatively biased, highly positively biased. Coverage probability is pretty horrible. If you don't do an evaluation, you don't do a calibration exercise, as what Martijn showed yesterday, you can get yourself in real trouble with this design. So even though we're presenting it, we're going to present basically the best of what people are currently doing right now. Don't think that you're like home free if you just follow these steps. Quite the contrary. Okay. Okay. So framing language here. A cohort. I'm going to define a specific definition of the word cohort that we're going to use throughout the day. A cohort is a set of persons who satisfy one or more inclusion criteria for a duration of time. Okay. So a person can belong to so here's the consequences. A person can belong to multiple cohorts. That's totally fair game. If they satisfy different criteria, that's okay. One person can belong to the same cohort multiple times as long as it's in different time intervals. So someone could join a cohort, leave a cohort, come back to the cohort. One person may not belong to the same cohort during the same period of time, though. So you're either in or you're out. That's a binary state. One cohort might have 0 or more members. So it's actually totally valid to define a real population and that population have nobody in it. We actually see this happen in the OHDSI studies quite often, where I define a valid cohort definition that works in my database. I give it to Adler, and in Columbia they have no members. It does not mean my cohort definition is wrong, it just means that nobody in Columbia satisfies that criteria. Okay. And snarky comment here, a code set is not a cohort. So many times you'll read a paper and it says my cohort was defined as ICD-9 433, 434, 436. That's not a cohort. You actually need to provide the logic for how a code set would actually be used. It's totally valid to say we looked for the first occurrence in a claim of an ICD-9 code 433 and the person was followed for some period of time, but you can't just tell me a list of codes and expect that that's a cohort. That's what a definition of a cohort, that's how we're going to use it throughout the day. I'm going to say that we're going to go through, to Anna's question, we're going to go through how does one actually explicitly define cohorts, and we're going to go through, in the designer session, we're going to go through a tool-based approach to how you can formalize the definition of a cohort. So stay tuned for that. Important thing is that as we're working with databases, databases can have lots of different cohorts. Cohorts could be new users of drugs, they could be procedures, they could be devices, they can be outcomes, they can be diseases, they can be combinations. People can belong to many different cohorts, and that's all fine and good. What we are going to do for purposes of a comparative cohort design is simplify our decision making and our structure of all of those questions back there by saying that your job is to define 3 cohorts, 1 parameter, and 1 model. Those 3 cohorts are your target cohort, your comparator cohort, and your outcome cohort. Once you have defined those 3 cohorts, we're going to talk about a time at risk. That is going to be the time that members of your target and comparator cohort would be at risk for then appearing in your outcome cohort. And then we're going to define a model specification, which is going to be what research question you're going to answer given that you've got these cohorts. So one of the exercises I want you to all be thinking about for your questions and throughout the day is we're going to want you to be able to fill out this table for yourself. If you've got a piece of paper, you can start jotting it down. But you're going to hear me say it over and over again. What's your T? What's your C? What's your O? And as we review these papers, I want you to think very clearly about what this is. To Anna's question, defining these cohorts precisely and specifically is one of the key challenges of this design, and we need to make sure that we're all doing that appropriately.
So is T is blue and C is red, or I have to pick, I will call one of the colors as my target?
Yeah, so if you want to think about the red pill and the blue pill, think of one of those as your red pill, one of those as your blue pill. Yep. Okay. So when we do a cohort analysis, we're going to start with our initial cohort T. There might be some qualifying patients that we restrict ourselves down to for various reasons. There'll be a comparator cohort C, and we're going to restrict ourselves down. We will then produce analytic cohorts, which are going to be even further subsets. So for example, if I want to compare people on the red pill versus people on the blue pill, I might, for purposes of this study, have to exclude anybody who took the red pill and the blue pill. Because if I took both, I wouldn't know what to do. So we might have to have further restrictions due to the specific analysis question that we're going to answer. From there, there's going to be independently this definition of an outcome. And really the research question is going to become, amongst the people in your analytic cohort T prime and your comparator cohort C prime, we're going to look during that time at risk window to see whether or not these people belonged to your outcome cohort. This framing is how we're going to be thinking about things for the day. I just want to orient you a little bit to how this is different. Sometimes when people think or conceptualize about a design, they think only of the outcomes that would happen to these people. So they're thinking about this kind of this overlapping region. That is, they're saying, I'll pick on Nicole again. So the outcome is urinary tract infections. We should be able to come up with a common phenotype for urinary tract infections independent of SGLT2 and DPP4. Urinary tract infection is just a disease. We should just be able to find those people. But sometimes when people design comparative cohort studies, they conflate the exposure and the outcome as part of the definition. So they start to say the outcome will be UTIs following exposure to SGLT2. So they actually construct a cohort which is the UTIs after exposure to the treatment group. We're going to define it independently. Our analysis is going to, of course, use your time at risk window, use your model specification to find the right people. But the point that I want to impress upon you is if we develop a standard definition for UTI, then now if you want to change your question, say now you want to do SSRIs and SNRIs for UTI, you have a common outcome cohort that you could apply to different research questions. Okay.
Yeah, it's a question.
Okay. All right. In behind. Okay. Yes. Okay. So I've covered the cohorts. You got to think about what's your T, what's your C, what's your O. I covered time at risk. It's the period of time that you're going to look to be in O after being in T or C. Your last thing is that you need to choose a model. Okay? The model that's going to give you this causal inference. So there are 3 different models that we're going to focus on today. And the point that I want to make here is that as you choose a model, the model is going to really be guided by what your research question is. Or if I want to flip that over, if you tell me your model, I can tell you your research question. Very often what we see is someone writes a research question down and then chooses a model. And sometimes the model they choose isn't consistent with the research question that they had in mind. So let's, just to make this a one-to-one mapping, let's think about what you've been doing. We've got 3 different kinds of models that you could study for your questions. We have a logistic regression, a Poisson regression, and a Cox proportional hazards. For a logistic regression, what we're talking about is a binary classification of did people have the outcome or not in some fixed period of time. Okay, so you're just, for any of your questions, if you're thinking about your question right now, if you're just going to ask the question, I'll keep picking on Nicole since I can say UTI without knowing anything. So if it's just, did you have a UTI, yes or no, a logistic regression can work out. The metric that will come from a logistic regression is an odds ratio. A key assumption here is that there's a constant probability across that fixed window. So you have to have a fixed interval that you're following if you want to apply this. But a totally valid thing to do. Second model here is Poisson regression. Here what you can think about is counting the number of occurrences of an outcome during the time at risk. Okay? So running with Nicole's example, it might be the question, right now it just says the risk of UTI. We haven't specified what the model is. First one would have been, did they have a UTI, yes or no? This might be, how many UTIs did they have during their time at risk? With a Poisson regression, you're going to get a rate ratio. You're going to be able to have a ratio of incidence rates. Key here is that the outcomes follow a Poisson distribution with a constant risk during, in that time interval. The last model is a Cox proportional hazard model. Here what we're doing is we're computing the time at risk, the time to event during your time at risk window. We're tracking censoring events, so someone might leave during their time at risk. In this context, the key metric that you're going to get out of a Cox proportional hazard model is a hazard ratio. And there is an assumption here being made about proportionality that you have to pay attention to make sure these groups are adequately represented. In this case, the question would now really be about SGLT2s and DB4s is, what's the hazards of having a UTI following them over some duration of time? These choices, these are the 3 that we're going to focus on, and for pharmacoepidemiology anyway, this covers 99-point-some% of what you're actually going to see in the literature. There was a comment yesterday, and I heard, I guess in the prior conversation, this question about are there other things you could do? I guess it's for your question. If you're thinking about a continuous variable, these models would not be applicable. Okay? So for purposes of today's exercise, what I encourage you to do is, if you're thinking about change, was it blood pressure? Heart rate or something like that. So what you could think about is how would you take that continuous variable and turn it into, did it go up? Or how many times did it go up? Or time till it went up? There was ways you'd be able to take that continuous variable into it. There are other models for handling continuous variables that's out of scope for today. Yes?
I was just wondering, why are you limiting to the proportionality? So, in our example, short-term survival could be very different from long-term survival given the treatment. So proportionality is not a good assumption here. It's violated clearly. So why are you?
I'm just highlighting what the assumption is. You need to think about that as you're interpreting your results. What could the potential biases be given that you don't believe that you're going to satisfy the proportionality assumption?
But where do you need it? Why do you need a proportionality?
You don't. So there's nothing. We're agnostic about what's in these three columns. They're just three examples of models we happen to be focusing on today. But absolutely, you could add a fourth column, which is an additive survival model or whatever. Just we're not doing it today. We're not saying make a proportionality assumption.
That's right. Yes, absolutely not. Yeah, I'm not advocating. But I do want to make it very clear. You all today need to make a choice of one of these three.
As a practical matter.
And if you want to use the OHDSI tools, this is what's going to be available to you right now, and it covers most everything that everybody's doing. But consciously, when you make one of these choices, you are choosing a model that is now defining what your research question is. And you need to be very, very clear that that's what's happening. Another paper I'm just referencing, McElhernan talks about if you're trying to emulate a randomized trial by using an observational data, what you should do is just follow best practices. I don't disagree with that. What he talks about is make sure you define your eligibility criteria, treatments, strategies, assignment procedures, follow-up period, outcome. Basically what we've just walked through is he's saying you do that in a good, well-designed randomized trial. Why not do it in an observational study? We agree. Okay, so going back to this picture, actually, and this is actually going to be my key stopping point here. We want to standardize the end-to-end process. Your research question, you guys are responsible for the review. That design requires complete specification of all the choices. You all need to decide on your T, your C, your O, your time at risk, and your model specification. You make those choices in your design. You produce a document that says those are the choices that I am making. If you make those choices, and we're going to go through all of the details of those choices, then one should be able to, anybody in the world should be able to unambiguously pick up your document and write code that's fully reproducible to execute that study. And if it's done in an appropriate framework, we can then evaluate, and then you can publish your papers. Okay? In the interest of time, I'm not going to go through any of those guys. But I'm going to end with one thing. We want you to take your questions and publish them. Okay? So here's how I want you to think about why you should be following this framework. If you're doing your design section, you're doing your review is the background section of your paper. That silly paragraph that says, my question hasn't been answered yet. You got to do that anyway, so write that up in your protocol. Your design is the method section. The only thing you should have to do is that when you write your protocol, you should write it with verbs that are in future state. We will do the following. When you write your paper, you'll say, we did the following. There should be no deviation from what we will to what we did. Those should be the same thing. You should only change the tense of your verb if you do this correctly. When you execute, you're going to generate results, standardized results, what Martijn showed yesterday. Basically, if you run these tools, your results section is written for you. You should evaluate, and the evaluation should be part of the results. This is something we don't see. Even when Martijn talked about diagnostics, oftentimes people, I think, use diagnostics internally for themselves to get confident that they understand something, but they don't share the diagnostics. We would argue that all of your diagnostics are part of the evaluation and are in fact part of the results of your paper. And once you do your synthesis, you should write a discussion, and hopefully your discussion does not end with the sentence, more well-designed studies should be done. Our goal is to help those of you that are the designer track. We're going to get you through writing a protocol, and Martijn and that's what David and I are going to walk you through for our breakout. And what Mark and Martijn are going to walk you through is how to actually take a design, anyone's design, and be able to execute it. So, I want you all to be thinking about it, and at the end of today, I want to see a piece of paper or something on your screen where you can confidently tell me what's your T, what's your C, what's your O, what's your time at risk, and what's your model specification. So, let me stop there, right on time. Questions, comments, reactions? This framework makes sense?
Okay, so I just had a question about that Venn diagram slide that you had with the two cohort, with
Yep.
the whole. Okay, so I just want to confirm that the overall cohort from which these two groups have been pulled. So basically, any eligibility criteria we apply applies to that overall cohort.
I'm not going to talk about it that way, Urmila. But if you want to think about it that way, I do want to be very precise about this. You're going to define two cohorts, a T cohort and a C cohort. If you want to think about that there's one magical underlying cohort, think of it as the union of T and C. So if you wanted to actually physically instantiate that cohort, you would say, get me all of the people in T and all of the people in C. And that would be your underlying cohort that you're going to work off.
Okay,
But
actually,
in this exercise, you don't actually need to do that. You don't need to describe that. You don't need to execute it. You just need to give me a T and a C.
Okay, because the only reason I was thinking of that is to ensure that we have the counterfactual ideal, that we are not applying separate eligibility criteria to the target cohort and separate to the, because at the end of the day, the only thing that we hope would be different is the exposure. So which means any inclusion exclusion criteria, I mean, all else, we have to be similar.
Yeah, it's a very good point. So our exercise throughout today is to try to draw a valid causal construct. So what we're going to try to do is strive to make the people in T as similar to the people in C as possible. One way that you can do that is to apply inclusion criteria in your cohort definitions. And presumably, if T has to satisfy one set of criteria, then you probably want those same criteria to be applied to C. It is not always the case that you must do that. And in fact, there are lots of examples in the paper where people don't do that, probably inappropriately. But it is not a hard constraint that one does that. In fact, actually, as we go through our exercise, we gave you 2 papers to read. And I want you to specifically be reading that and paying attention, because you're going to at least see one example where they didn't do that.
Yes, I did see that, and which is what I didn't totally agree with, because it's not a, it's not a great counterfactual.
Yeah. So that's exactly what we're hoping that you were going to find. What I will say, and actually as we show you the designer activity, one of the things we've done in our tool very explicitly, and as we walk through it, is what I like to do as a best practice is I create my definition of T, which is, let's say it's a drug, let's say it's the drug study. I create my definition of new users of of the red pill with all of the following inclusion criteria. I literally take that criteria, physically copy it, and only make one change.
Okay.
I switch red to blue. And that's my best practice for ensuring that all of those criteria are the same.
Okay.
But
an even better practice would be to make one concept, which is everything but the drug, and then T and C include that concept and their specific drug, so there's no duplication.
yeah, so if you want to frame what that population
Yeah, because if, for example, you go back and you change T, currently you have to also remember to change C. But
So-
if you're just dependent on a single concept.
There are numerous examples, some of which I would agree with Urmila are questionable reasons why these inclusion criteria would be different. Others are actually valid considerations. Actually, and I think even for example, thinking about whether it's okay to, if you've got 2 different drugs that you're comparing, one group might say, have a criteria of you can't have had prior C, but for group C you don't have to can't have prior T. So there are situations where the criteria of which people get excluded are you going to stay in this group or not can be different, and some of those are valid. But your point is spot on, and everybody should pay very close attention. We're trying to make that causal inference as valid as possible. That means making these groups as similar as possible because we're trying to emulate the DeLorean. Okay, any other questions, comments? Vivian.
Back to your diagram of the steps of the research, the evaluation part, because you were saying evaluation including your results. I would think because usually we do your regular steps, you have your results after you program that, right? Right now we use the tools. So how do we evaluate those results? Is that extra step or just that?
Yeah, so it's an extra step. So what you saw from our time, for example, and one of the things we're gonna get on in the further exercises, the use of negative controls is a strategy for evaluation. But the point and the key here is that if you design your study appropriately, the evaluation is nothing more than using your design for a referent situation, like a negative control. So swap out your O for a negative control O, run the study, and you can see how much you can trust it. And so all of the evaluations are just metrics that come out of using that exact piece of code and testing how it works. Which
So I have a question for the Cox model. If I have my T, C, and L, then I need one for censoring patients with drug cancer at some point, or something else. How do I deal with that aspect for that one?
So we'll get into specifically how you would implement that, but think of that as part of your cohort definition. Remember, your cohort is a set of criteria for a duration of time. So what you're talking about is the exit criteria. When would you leave the cohort?
When do you leave the outcome?
So you would leave once you got cancer, for example. That would be your censoring event. And so you'll be able to follow someone while they're in their cohort, but if they have one of those disqualifying events, they'll leave the cohort for that reason.
But I would almost, they would leave the whole experiment even if they don't experience the outcome. If outcome is like an adverse event, let's say to becoming blind, that's the outcome. But they also get cancer, which so much confound my study. So should I add that thing to TNC?
So you have options, design choices you get to make. One is you could say, I don't want those people to even be considered for the study at all, in which case it would be an inclusion criteria to exclude them from your populations. The other option is you think of it not as,
they can still be in it.
that's right, so you might want to keep the people in the cohort, but censor their cohort or exit time. So they will stay in your cohort until some moment that they've had a censoring event. So both of those are design options that we'll walk through each specific example.